Hola, buenas tardes. Es un enorme gusto que nos acompañen, deseando que se encuentren de lo mejor. A nombre de la Asociación Mexicana de Especialistas en Nutrición Animal, les doy la más cordial bienvenida. Como ustedes saben, la AMENA se ha planteado como objetivo el continuar intensivamente con la difusión del conocimiento mediante la presentación de trabajos de gran calidad por este medio virtual. El día de hoy tenemos el gusto de contar con nosotros con el doctor Carl Parsons, quien por muchos años ha sido uno de los líderes internacionales en la generación y difusión de la ciencia avícola desde la Universidad de Illinois. Preocupado por la sustentabilidad en las fuentes de alimentación de este sector, está dirigiendo una serie de investigaciones encaminadas a evaluar las diferentes alternativas. Esta tarde nos presenta algunas conclusiones sobre el valor nutricional de la harina de insectos en dietas para aves. La AMENA le agradece profundamente al Dr. Parsons por esta ponencia. Esta charla será en inglés, por lo que contamos con traducción simultánea, a la cual pueden acceder en la parte posterior derecha del menú, en el icono de interpretación. Es un mundito pequeño. Otra gran persona de esta misma universidad es el doctor Sergio Fernández Tinoco, quien estará haciendo el trabajo de moderación, a quien igualmente mucho le agradecemos por ello. Las preguntas y respuestas, bueno, más bien las preguntas se estarán haciendo por el icono de preguntas y respuestas, questions and answers, que tienen también al fondo, casi a la izquierda. Por último, queremos reconocer y agradecer a la compañía Elanco por su amable patrocinio para la realización de este evento. Sergio, te dejo en el mando del evento y muchas gracias.
Muchas gracias, Pancho. Buenas tardes a todos. Pues voy a proceder a comentar un poco el currículum del doctor Parsons, que es bastante extenso, pero voy a hacer un resumen. No sé si pueden ver mi pantalla, si no lo voy a comentar. El doctor Parsons es investigador y profesor de la Universidad de Illinois. Él hizo una licenciatura en Agricultura General en la Universidad de Maryland. Después obtuvo su maestría en el 78 del Instituto Politécnico de Virginia, y también obtuvo el doctorado en la misma universidad. Él es profesor en la Universidad de Illinois desde 1981, siendo ya en 1992 alcanzó la definitividad o el tenure que le llaman ya profesor inamovible en la universidad. Él es profesor de 6 cátedras, todas relacionadas con la nutrición avícola. En cuanto a sus honores y actividades profesionales, son bastantes. Uno de los más interesantes que vi, sus estudiantes han ganado 13 veces los premios a las mejores presentaciones de trabajo en Poultry Science, ¿sí? Y también el doctor ha publicado 11 capítulos de libro, tiene 245 artículos publicados en revistas con comité editorial, 65 proceedings, 252 abstracts, y ha sido miembro de la mesa directiva tanto de Poultry Science como de Journal of Applied Poultry Research. Es miembro de la Asociación de Poultry Science y es miembro también de World Poultry Science Association. Él ha graduado 30 estudiantes de maestría y 14 estudiantes de doctorado, y hay mucha gente que está en la industria. Por ejemplo, Amy Batal es la nutrióloga corporativa de Sanderson Farms, la tercera productora de pollo más grande de Estados Unidos. También tiene a Rob Shirley de Addition, Janet Snow de Devenish, Kim Livingston, que está en el ANCO, Carlos Martínez, que es profesor de nutrición, Stephanie Frankenbach y Chris Hansen, Leonel Mejía Stenkov, Mike Pearce es profesor de Virginia Tech, y bueno, un servidor. Yo también fui estudiante del doctor Parsons. Entonces, sin más, los dejo con él. Please, Carl, you can take over.
Get that out of there. All right, share screen. Yes, and okay. Hopefully everyone can see the slide. Thank you very much, Sergio, for that very nice introduction. And thank you to the committee and everyone for inviting me to talk to you today about some of our recent research with insect meals for poultry nutrition. First, I would like to acknowledge my master's student, Nahal Mateen. This was her thesis research, so she deserves most of the credit because she did most of the work. All right, a little background. We all know that as the global worldwide human population increases, we're going to need to produce more food. And so we need new innovative ideas on how to do that. And one of the possibilities is the use of insect meals in animal feed diets. Most of our protein sources today, of course, are plant and animal meal based, but those have some food security and environmental concerns. So an alternative protein source, or at least an additional protein source possibility in the future, are insect meals. They are very abundant. They have low environmental impact. And generally, most of them are quite high in many nutrients. One of the most popular candidates for insect meals is the black soldier fly larvae, abbreviated BSFL. It can feed on many different types of organic materials, and it empties out its GI tract in the prepubertal stage and then stops all feed consumption as an adult. The little bit of research that has been done shows that it has a proximal composition pretty similar to soybean meal and also somewhat similar to fish meal. It can be quite high in calcium at times. And the one or two studies that have been done have also shown that it seems to have fairly high amino acid digestibility and metabolizable energy. Another insect meal that is of interest is cricket meal. And it's greatly impacted by its nutritional composition of the diet. It oftentimes may be high in sodium. And one study that has been done suggested that methionine and arginine were co-limiting when fed to broiler chickens. Now, a third insect meal that we have worked with and is a possibility are the mealworms. They are the larval form of the darkling beetle, and they tend to be high in protein, very high in fat, and also contains certain levels of minerals, but are generally low in calcium. And looks like it may have a protein quality pretty similar to soybean meal. Now, there's also other insect meals, many insect meals that are some researchers have evaluated, such as grasshoppers, locusts, earthworms, and silkworms. But the three that I mentioned earlier are the ones that are basically getting the most attention and seem to have the most potential for future use in poultry diets. Now, I think and one thing that's interesting here is that we really do not know much of anything about the availability of phosphorus in insect meals. I think we know well know that approximately only 1/3 of the phosphorus in plant ingredients is non-phytate phosphorus that's available. Insect meals contain a substantial amount of phosphorus, but we have not been able to find much of anything in the literature indicating whether most of that phosphorus is available or not. And there's different methods of evaluating that, such as the relative availability method or the digestibility or total tract excreta retention methods. And I'll talk more about those later. So in our studies with the insect meals, we conducted 8 total experiments. The first 6 experiments were with our precision-fed rooster assay. And the last 2 experiments were chick assays, one with commercial broiler chicks and one with our special genetic line of crossbred chicks that we have at the University of Illinois. The overall objectives was to compare the nutritional value of 4 black soldier fly larvae samples, 1 cricket meal, and 2 types of mealworms. The objective was to determine the true metabolizable energy and also the standardized amino acid digestibility, again, using our precision-fed rooster assay. And in addition to the rooster assays, we also conducted 2 experiments to determine the digestibility and the bioavailability of phosphorus in 2 of the black soldier fly larvae samples and a partially defatted black soldier fly larvae in the 2 chick assays. Statistical analysis was, for most of the experiments, was pretty simple and straightforward. Just analyze one-way analysis of variance for completely randomized designs and use the least significant difference test to determine differences among treatments with a probability of 0.05. However, in the last experiment that I will discuss, the relative phosphorus availability experiment, we used a multiple linear regression approach where we basically take total tibia ash or tibia ash as a percent as our response parameter, and then we determine bioavailability of the phosphorus in the insect meals using the slope ratio method relative to potassium phosphate. So, and we set the bioavailability of the potassium phosphate at 100%, and then we calculate the relative bioavailability of the phosphorus in the insect meals compared with the potassium phosphate. And I'll discuss that more in detail later. So we start with the rooster assays. We conducted 6 of those to evaluate amino acid digestibility and true metabolizable energy of 7 insect meals. Okay, for our precision-fed rooster assay, we use conventional roosters to determine true metabolizable energy, corrected to 0 nitrogen retention. But then we use susceptimized roosters to determine standardized amino acid digestibility. I think most of the people in the audience are probably familiar with this technique, but just to review quickly, we generally fast the roosters for about 26 hours to empty the digestive tract. Then we crop intubate or tube feed the insect meals, usually 25 to 30 grams. Put the bird in a cage and then collect quantitatively all of the excreta, urine plus feces, that are voided during the next 48 hours. So for experiment 1, that was to determine the TME of 2 different black soldier fly larvae, 1 and 2. So we precision fed or tube fed 25 to 30 grams. We had 8 individual roosters caged per treatment ingredient. And experiment 2 was basically the same as experiment 1, but we measured standardized amino acid digestibility of the same 2 black soldier fly larvae meals using cystectomized roosters. Again, we use cystectomized roosters that have surgically had their ceca removed so that we can get more accurate amino acid digestibility values. So so now turning to the results of experiment 1, looking at the analyzed composition and the true metabolizable energy of the first 2 black soldier fly larvae. So here we have the crude protein. You can see it was similar, high, about 58% in the 2 meals. Fat was also high, about 20%. NDF was moderate, 12 to 15% neutral detergent fiber. You can see quite a bit of variation in calcium. 1.34 in one, 2.28 in the other. Phosphorus was pretty consistent in sodium. Both of the meals had high true metabolizable energy, at 4,000 or more kilocalories per kilogram on a dry matter basis. So rooster experiment 2 was conducted for amino acid digestibility for those first 2 black soldier fly larvae meals. Here I am just showing the results for 4 of the more important amino acids: methionine, cysteine, lysine, and threonine. And you can see generally looking at methionine, lysine, threonine, the digestibility is quite high, around 90% or more. Cysteine is slightly lower, which is pretty typical that we see there. And it was pretty consistent between the 2 meals, significantly slightly lower for the second sample than the first one, but still fairly consistent. So experiments 3 and 4 were the next 2 rooster assays, where we evaluated black soldier fly larvae 3 and a cricket meal. Now the cricket meal, we did tube feed that mixed with corn because it was difficult to feed because of its physical nature. 6 roosters per treatment. And then experiment 4 was another rooster assay, exactly the same as experiment 3, except using cystectomized roosters to determine standardized amino acid digestibility. So the results for experiment 3, for the black soldier fly larvae 3 and the cricket meal. So the black soldier fly 3, again, high in protein, 45%, but the cricket meal was even higher, 67%. Crude fat was again around 20% for the black soldier fly larvae meal, and basically about the same thing for the cricket meal. NDF fiber, about the same, not but difference 33, 36%. Notice here, this black soldier fly 3 was very high in calcium, 3.65%, whereas the cricket meal was quite low in calcium. Phosphorus, total phosphorus was similar. The cricket meal, as I mentioned earlier, they are often higher in sodium. And so this one was, again, much higher in sodium than the black soldier fly. But both of them had high metabolizable energy values. Again, values of 4,000 or higher per kilogram. So rooster experiment 4 now, amino acid digestibility of the black soldier fly 3 and the cricket meal. Again, just showing the 4 amino acids here. Again, the black soldier fly larvae meal here, 3, very high digestibility, around 90%. And actually for the cricket meal, it was quite similar, again, quite high, maybe slightly lower in some cases. So again, fairly high amino acid digestibility for both the black soldier fly and the cricket meal. A little lower for cysteine, as we showed in the previous graph. So turning now to the last two rooster assays. Experiment 5 determined TME, again, this time for a partially defatted, lower fat black soldier fly larvae meal, and also two different mealworms. We only fed 20 grams of the mealworms because of their bulkiness. 6 roosters per treatment, individually caged. Similar methods, experiment 6 to experiment 5, except again, we used cystectomized roosters to determine standardized amino acid digestibility. So partially defatted black soldier fly and 2 mealworms. So the results for the analyzed composition and the TME of these ingredients or samples. So for the partially defatted black soldier fly larvae, high in protein, as we've seen before, about 57%. A little lower in fat, down around 12% compared to more like about 20% for the others, but it was partially defatted, so that makes sense. Now the mealworms are also high in protein, 50 to 56%, very high in fat, about 30%. Fiber, you can see here the mealworms are lower in fiber, NDF, much lower in calcium than the black soldier fly larvae. Phosphorus, total phosphorus, not greatly different, and sodium was lowest, a little lower in the mealworms. Again, the partially defatted black or soldier fly, it was a little lower in metabolizable energy than the previous black soldier fly larvae, but that's expected because it was partially defatted and lower in fat. The mealworms were very high in energy, over 5,000 kilocalories per kilogram. So rooster experiment 6, as before, determined same experiment, just determined amino acid digestibility rather than TME using cystectomized roosters. And here's the results for the same 4 amino acids that I've shown earlier. And for all the meals, generally, again, fairly high amino acid digestibility. As you can see, methionine, lysine, threonine, all up around 90% or higher. Again, a little lower for cysteine, but all fair. And again, all the meals were fairly similar. So again, we see a pretty consistent high amino acid digestibility for most all of these insect meals. So just to summarize the rooster assays quickly. TME first, for the first three black soldier fly larvae meals, TMEs were high, like around approximately 4,000 kilocalories per kilogram. A little lower for the partially defatted black soldier fly larvae, which you would expect because they had removed some more of the fat. Cricket meal was high, pretty similar to the black soldier fly larvae meals. The mealworms were really high because of their high fat content, up around 5,000. And this is just a comparison to soybean meal here on the right. You can see that all of the insect meals contain substantially higher levels of metabolizable energy than soybean meal. Now here's a summary here looking at digestible amino acid concentrations across the different meals. And this is when you take the total amino acid content of the ingredient multiplied by its digestibility value. So this would be the value that would be used in commercial feed formulation in the linear program computer matrix. And you can see for methionine plus cysteine, fairly consistent results across the different meals. And the values are fairly similar to soybean meal. They're all around 1.4, to 1.5% digestible methionine plus cysteine in these meals. Lysine summary, Similar type of thing for the black soldier fly, partially defatted and cricket meal. Quite high levels of digestible lysine, much higher than for the mealworms and for the soybean meal, which were both similar. So again, most of these meals had quite high digestible lysine values. Just again, to just mention threonine, fairly consistent across all insect meals and soybean meal. Everything compares quite about the same, around 2% or 2.2% digestible threonine. So overall conclusions, there was some variability in the nutrient composition among the different insect meals with regard to protein, fat, and particularly calcium. But generally all had high TME levels for all the insect meals, with the black soldier fly averaging around 4,000 and the mealworms above 5,000. And so these are similar to or higher than pretty much most all of the plant and animal-based conventional feed ingredients that we have. So they compare quite favorably with the types of ingredients that we currently have available and are using. Continuing on now with amino acid digestibility summary, again, high digestibility for most amino acids in the black soldier fly larvae and mealworms, 85 to 95%. Little lower digestibility for the cricket meal for some amino acids compared to the other insect meals. But again, these values compare quite well, or oftentimes are even higher than the values that we typically see for something like soybean meal, which is a primary protein source in most poultry diets. So the last part of the study now was to evaluate phosphorus availability or phosphorus digestibility in these different insect meals. As I mentioned, we can't find really much data, hardly any data in the literature on this subject at all. So we set about to try and determine ileal phosphorus digestibility and excretive phosphorus retention, or some people would refer to this as total tract phosphorus retention values for the 3 insect meals. So this was the first chick experiment that we conducted. We used commercial broiler chicks. I think they were probably Ross 308 or 708s. I don't remember. We had 3 dietary treatments. We had the black soldier fly 1, black soldier fly 3, and the partially defatted black soldier fly. 8 replicates per treatment and 5 chicks per pen or per replicate. Now, the way this study was conducted is that during the first 18 days of the experiment, all of the chicks were fed the same nutritionally complete corn, soybean meal pretest diet. On day 19, the chicks were weighed and allotted to the dietary treatments. And the 3 dietary treatments were 3 diets containing either 27% black soldier fly larvae 1, 30% black soldier fly larvae 3, or 30% partially defatted black soldier fly larvae. And the insect meals provided the only source of phosphorus in the diet. So they were fed for 4 days. Day 22, at the end of the experiment, the chicks were weighed, killed, and then we collected the ileodigesta from the GI tract, from Meckel's diverticulum to the ileocecal junction, so we could measure ileal phosphorus digestibility. And we also collected the urine and the feces, or the excreta, from day 21 to 22, so we could determine excretive phosphorus retention or total tract phosphorus retention. Now, the base ingredients for all the diets was a little bit of soybean oil, 10% cornstarch, a little bit of sulcoflock cellulose. These were basically semi-purified diets, vitamins and minerals. And the majority of the diet was made up of the insect meals or dextrose. So these were basically dextrose insect meals diets with a little bit of, about 10% cornstarch. And then again, we had these levels of the black soldier fly larvae in the diet, and they were added at those levels to provide approximately 0.25% phosphorus from each of the insect meals. For diet 1 and diet 3, we kept the calcium constant at 0.35%. But diet 2, the calcium went all the way up to 1.07%. And that was simply because, if you remember, diet 2 contains the black soldier fly larvae 3 here at 30.38%. And that particular insect meal was very high in calcium, 3.65%. So then the calcium level was higher for that diet, and there really was nothing we could do about that. Okay. So then for the results. So again, we determined ileophosphorus digestibility from collecting the ileodigesta. And then we determined excreta phosphorus retention or total tract phosphorus retention from collecting the urine and the feces. And you can see here that for the black soldier fly larvae 1 and the partially defatted black soldier fly larvae, the ileophosphorus digestibility and the excreta phosphorus retention values were quite high, around 85 to 89%. For black soldier fly 3, the phosphorus digestibility and retention values were somewhat lower, about 73 to 75%. So then the last study that was conducted for the project was to determine the availability of the phosphorus in the 3 insect meals relative to potassium phosphate. So this is using a different approach. It's a type of assay that we have used many times in my lab in the last 40 years, where we determine relative phosphorus availability based on bone ash. And we actually like this assay better than the digestibility assay because we get more consistent and more believable results. So for this study, we used a New Hampshire by Columbian or crossbred chicks simply because these types of birds are more uniform and they will eat these semi-purified diets better than commercial birds will. We had 9 dietary treatments, 5 reps of 5 chicks per pen per treatment. The overall basic design of the experiment was that we fed all the chicks the same nutritionally complete corn soybean meal pretest diet for the first week, day 1 to 7. Chicks were then weighed and allotted to dietary treatments. And then they were fed one of the 9 diets, experimental diets, for 2 weeks from day 8 to 22 weeks of age. At day 22, the chicks were killed, and we took the right tibia bone from each chick. We autoclaved it, cleaned it of all tissue, oven dried it, and then ashed it in a muffle furnace to determine bone ash for 24 hours. And then we expressed our data for bone ash either as milligrams per tibia, the total milligrams of ash in the tibia bone, or as a concentration, bone ash percent, as a concentration in the bone. And then we calculate relative bioavailability of the phosphorus in the insect meals compared with potassium phosphate. So these are the diets. The first 3 diets, we start off with a phosphorus deficient corn dextrose soybean meal diet containing only 0.14% NPP or non-phytate phosphorus. So it's quite deficient. Then we add 0.05% supplemental phosphate from potassium phosphate. Diet 3, we add 0.1% phosphorus from potassium phosphate. This is our standard curve. Then for diets 4 and 5, 6 and 7, 8 and 9, we add increasing levels of the 3 black soldier fly larvae. So if diet 4 has 7% black soldier fly larvae, diet 5, 14%, then diet 6 has 8% black soldier fly larvae 3, and diet 7 has 16%. And then diet 8 and 9 have 8 and 16% of the partially defatted black soldier fly larvae. And these are all added in place of cornstarch. So the base ingredients across the diet, like I mentioned, it's a dextrose soybean meal diet. It has about 42% soybean meal in there, 5% soybean oil, and then some vitamins and minerals, etc. So then the diets, the first 3 diets are the standard curve diets where we had no added potassium phosphate, or we add 2 levels, increasing levels of potassium phosphate to provide 0.05 and 0.1% supplemental phosphorus. And again, these are basically cornstarch, dextrose diet-based diets with, like I mentioned before, the soybean meal in there. Now for the insect meals, again, for black soldier fly larvae 1, we added 7 and 14% black soldier fly larvae in diets 4 and 5 in place of cornstarch and dextrose. And then we tried to adjust all the diets to maintain a 0.8% calculated dietary calcium level in the diets. 6 and 7 are similar, same type of thing. 8 and 16% black soldier fly larvae 3, again added in place of the cornstarch and dextrose, and then adjusting the limestone to keep the calcium constant at 0.8%. Diet 8 and 9, again, same thing, except we use partially defatted black soldier fly larvae, added at 8 and 16%. We're doing time-wise. Okay. So these are the results, and I'll show these in graph form here shortly, just because a lot of numbers. But you can see as we add, the first 3 diets have the potassium phosphate added. We see we get a nice linear response in bone ash, and we get a nice linear response to the black soldier fly larvae meals also. We go 250, 287, 330, and then 295 and 290, so we get a nice response both in bone ash as milligrams per tibia. And if you look at bone ash percent, you can see the same thing. Nice, nice linear response to adding the black soldier fly larvae meals. So then the results then are analyzed using a multiple regression approach. I'll mention the numbers just quickly here, and it'll be more clear, I think, when I show you the graph. But we regress tibia ash in milligrams on supplemental phosphorus intake from the potassium phosphate or the insect meals. And you generate a regression equation here where you have your y-intercept, and then you have a regression coefficient for the potassium phosphate in each of the 3 insect meals. And so then you calculate the relative bioavailability by dividing the regression coefficient for the insect meal by the regression coefficient for the potassium phosphate. In this case, it would be like 167 divided by 305. I think this will be more apparent when we look at the graph. So here's a graph of what is actually done. Again, we regress bone ash in milligrams per tibia on supplemental phosphorus intake from the potassium phosphate, from the black soldier fly larvae 1 and 3, and also the partially defatted black soldier fly larvae. And if everything works well, we should get a nice linear response, which we did to each one of the insect meals. The line with the highest slope or the steepest slope is the potassium phosphate, which we would expect because that phosphorus is basically 100% available. And you can see the insect meals or lines are lower than that, indicating that the phosphorus in the insect meals is not as highly available as the phosphorus in the potassium phosphate. And so then for the slope ratio calculation, we will divide these regression coefficients in the equation for each of these lines. We will divide these numbers by the slope of the line for the potassium phosphate to generate a relative bioavailability value. And these are the results that we received. And I think what we'll do is, well, I can show you, these are the total phosphorus values. These are the bioavailability values based on tibia ash in milligrams. These are the values based on concentration of the ash, and they're fairly similar. And if you want to multiply these values by the total to get the actual bioavailable phosphorus content, then you can do that. And I think we will move on to the graphs, which will be a little more clear. So these are the results here from the relative bioavailability calculations. So in this particular thing, we set the KH2PO4 at 100%. Assume that's 100% available. And then we calculate the bioavailability based on either tibia ash in milligrams or tibia ash as percent relative to the 100. And so when we do that, you can see that the values for black soldier fly 1 and 3 are pretty consistent. Whether you use tibia ash in milligrams or percent, the values are in the 55 to 50 to 60% range. And also fairly similar for the black soldier fly larvae that was partially defatted, although we had one value here that was 67. But again, we're looking at values that are in the 50 to 60% range. And like I said, if you want to calculate bioavailable content by multiplying the bioavailability values by the total phosphorus, we can see here as we look across here, whether you base it on tibia ash milligrams or tibia ash percent, we're getting somewhere around 0.5 to 0.6% bioavailable phosphorus in these black soldier fly larvae. So in summary, for the chick assays, we had fairly high ileophosphorus digestibility and excretophosphorus retention among all of the black soldier fly larvae meals. Generally values of about 80, close to 90%. For the one meal, it was a little lower at 74 to 75. The black soldier fly larvae 3 had the lowest value, and we think that was probably because of its high calcium content. And that's why it was lower than the other two meals, because we know high dietary calcium can negatively impact phosphorus absorption, retention. So that may be reason why we were getting the 73 and the 74% values for that particular meal compared to close to 90% for the other two meals. And then for the other chick assay, we did see a strong positive linear relationship between tibia ash and phosphorus from potassium phosphate and the black soldier fly larvae. Values were moderate for relative bioavailability, values of 55 to 65% in general. And these values were lower than what we got with the ileophosphorus digestibility and excretophosphorus retention, probably around 20 to 30% units lower for the relative bioavailability values than for the digestibility or excretophosphorus retention values. Again, we think that probably one reason for this may be that the diets in experiment 2, the relative bioavailability assay, were higher in calcium than the diets than most of the diets in experiment 1. So overall, to finish, we have the 7 insect meals all contained high levels of metabolizable energy and digestible amino acids. And the black soldier fly larvae also contained fairly high levels of bioavailable phosphorus based on ileophosphorus digestibility and excretion, about 20 to 30% lower for relative bioavailability if you base it, or for bioavailability if you base it on the relative bioavailability assay with bone ash, but still in the 50 to 60% range, indicating that all of the meals contain a substantial amount of available phosphorus for poultry. All right, thank you for your attention. And here we'll finish with a chicken eating an insect. So.
Muchas gracias, Dr. Parsons. Thanks a lot, Karen. I will have to ask these questions in Spanish. Anyway. Bueno, tenemos aquí algunas preguntas para el Dr. Parsons. La primera, ¿cuál fue el nivel de humedad de la harina de Black Soldier en los experimentos 1 y 2?
Yeah, humidity, that would be moisture. If I remember, they were pretty dry, so they would have been probably maybe 8 to 12%.
Okay. ¿Estas harinas se han probado en rumiantes?
I don't think so, but I don't know for sure. I don't, when Hall did her literature review, we probably she did not mention anything about ruminants. One problem might be with ruminants is these are all pretty high in fat. And I think that I'm not a ruminant nutrition, but if I remember from my ruminant nutrition classes in graduate school, that was only 45 years ago, but that high fat is not a good thing for the rumen.
Okay. ¿Conoce el costo de las harinas?
Right now, they're very expensive. I don't know what they haven't really been sharing much information on cost, but the last I heard, they were up in the $600 to $700 per ton range. So they were quite expensive. And so it's going to be a while yet before, if ever, they become, economically, for poultry. Hopefully they will as the industry gets bigger, but we will have to wait and see. But right now they're quite expensive.
Algunos países europeos como España han autorizado el cultivo y consumo de insectos para la alimentación humana. Conforme se extiende el uso, ¿se tendrán granjas de insectos diferenciadas para consumo humano y consumo animal?
Interesting question. I don't know, but I would think probably there's a good that probably that would happen if because usually there's much higher regulations for foods going into human food, things going into human food than to animal foods. So I think that person asked a good question, and I think there probably will be there probably will be separate farms, I think that would be designated for producing product for humans versus animals.
¿Qué proceso se utilizó para desgrasar parcialmente a la harina de insecto?
I did not do that. The company did that, and they did not share much information, but I believe they did it primarily by pressure. I'm pretty sure, because if they had used solvent extraction, you would have much lower level of fat than that. So I'm almost certain they did it by like an expeller pressing, some type of a mechanical pressing.
Actualmente es difícil para los productores orgánicos encontrar maíz, soya y otros ingredientes que se apeguen a esta definición orgánica. ¿Las harinas de insectos cumplen con la definición de orgánico?
Oh, good question. I don't do much work with the organic. I would assume that as long as, that's a good question, because I would think that they would, as long as they were fed an organic diet. My experience has been anything that's going to be fed in an organic diet has to be produced also organically. So it's, you know, so I would think if the insect meals were feeding on whatever they were being fed or whatever they were feeding on was organic, then they would, then I would think they would be suitable for an organic diet.
¿A qué se atribuye la menor digestibilidad del aminoácido cistina?
We see that in generally for most ingredients. So I think that has a lot to do with the cysteine and the cross-linking between the protein amino acid chains and the disulfide linkages. Now, in insect, so I think that's probably the reason. And we see that typically for almost all ingredients that you will usually see lower cysteine digestibility than you will for, say, lysine. Well, and as long as it's not heat damaged, then you will see lower cysteine digestibility than methionine, threonine, and lysine. Again, as long as the ingredient has not been heat damaged. And I think that's just because of the structure of the protein, the disulfide bonds, and the fact that it's somewhat difficult for the digestive enzymes sometimes to be able to attack the active sites around those disulfide linkages.
La proteína de insecto es muy cara para las fórmulas de alimentos en México. ¿Tendrá alguna recomendación para poderla usar?
Not at this time. It's too expensive to use it in the U.S. too. So I think we're just going to have to wait and watch the price, and to see if the price comes down, or if the price of soybean meal keeps going up, then I think it's right now it's an ingredient to watch for the future. We also know the future can change very rapidly after what's happened during the last year or so.
Otra pregunta acerca de rumiantes. Ya comentó que el alto nivel de grasa impide su uso, pero ¿se pudiera utilizar la harina de insecto parcialmente desgrasada en ovinos o caprinos?
Again, you're asking a poultry nutritionist or ruminant nutrition question, but I would say, yes, certainly. I think if I remember, the partially defatted was down around 12% fat. So I don't see any reason why at moderate levels it could not be used in a ruminant diet.
Okay. Una persona cuenta con un criadero de tenebrios con buena capacidad de producción y los alimenta vivo a sus aves. Él quisiera saber el método para convertir los insectos en harina. ¿Conoce alguna literatura que pueda ayudar para hacer este proceso?
Oh, I don't know. Right, if someone wanted to send me an email, we could check and see. I know earthworms or earthworm meal has been a little bit of research done on that. So I think that's a possibility. But I would have to, if someone could send that request in an email, I would check and see what literature we have in the file and see, because I know we have 2 or 3 review articles that cover almost every type of insect there has ever been in a type of meal. So there might be some information in one of those cited papers that would indicate how they actually did the processing to turn the worms into a meal.
Esta última no es pregunta, es una felicitación del doctor José Luis Laparra por la excelente presentación del doctor Parsons.
Oh, okay. Thank you. Thank you.
Carl, I have a question for you. Looking at the high level of TME that you found, do you have any idea about the fatty acid profile of these fats? Because we know that increasing the unsaturated fatty acids increases the TME. Do you know that, the fatty acid profile of these fats?
Oh, I think we did not do anything on the fatty acid profile part. I think I had in the slide, Sergio, that's pretty highly unsaturated, I think. And I know I have been contacted by 1 or 2 companies about the possibility of actually evaluating the metabolizable energy of the oil from some of these meals. But I think right now, again, I think the fact that they're so expensive, and I think a lot of the oils have some, I think, potential human health benefits, until the price of these things come down some, and so it looks like they have some possible economic, application to animals. I don't think there's going to, no one followed me up on actually doing any work yet. So.
Okay, thanks.
Yeah.
¿Qué puede comentar acerca de la calidad microbiológica de las salidas de larvas de mosca? ¿Cuáles fueron los sustratos sobre los que se producen las larvas de mosca?
I don't know anything about the microbiological thing. I know the meals that we got, I think they had been heat processed, and there was, they were not, I don't think there was any microbiological risk associated with those. As far as what they were, I think the question is, so as far as what they were feeding, I don't know. The companies have not been willing to provide very much information on that. I know sometimes, in some cases, they're actually feeding the insect meals poultry feed, and I know in some cases, but I don't really know what is that much about what they actually are using as their feed source in some of these plants.
Si los insectos se producen alimentándolos con excremento de ave, ¿es seguro alimentar a estos insectos a las aves?
Well, they were actually feeding them chicken feed, chicken poultry diets, not feces, I think is what that is what I was told. So it wasn't feces, but it was actually like, poultry diet or poultry feed that they were actually using in some cases.
Carl, I want to see the economics on this. If they are feeding poultry feed, some close to these insects, and then they feed the insects to poultry, you think that's economically feasible?
I think that might be, that's a good question. Yeah. I wonder how economical that would be. I guess apparently they're very efficient and they get a high protein yield from that, but that does sound to me like I always wondered. It seems to me like you'd be better off just to feed the chicken feed directly to the chickens rather than feed it to the insect. And I think, Sergio, that was probably only part of the diet that they were getting. I mean, it was probably like a supplement type of a thing. But that may be one reason why they're quite expensive at this time.
Okay.
Because I think everyone knows. I think it's easy to say that these insects can eat this and they can eat that and they can eat that, but it's kind of like the cellulose ethanol thing. Well, yeah, you can. I mean, the problem is that just because something will eat something, that doesn't mean you can be able to mass accumulate and mass transport enough of that efficiently to still wind up with an efficient overall operation. So.
Okay. Esta pregunta es un poco repetitiva. Si se alimentan las larvas con pollinasa o gallinasa, ¿es seguro para alimentar a las aves con harina de insectos alimentadas con pollinasa o gallinasa? Creo que
I think. Yeah, well, I said that I was talking about feed, but if you were to feed chicken manure, I don't think, I don't think that would pose, because once the chicken manure has been consumed by the insect and then traveled in through the insect's GI tract, then, I mean, I don't think that really in itself would cause a problem. I mean, we've often fed dried chicken manure to beef cattle and the ruminants in the past. And so I don't think that in itself would be, would be a health concern. Of course, you have to make sure that the manure has been, processed and dried, and not posing a health risk to the people who are working in the operation, but just feeding the manure to the insects and then feeding the insects to the poultry. I do not think that would in itself would cause necessarily cause a risk.
Okay. Hay más felicitaciones para el doctor Parsons por su excelente plática.
Oh, thank you. Enjoyed it. Thanks for the invitation.
Bueno, creo que ya se terminaron las preguntas y estamos llegando al final del tiempo. Entonces, doctor Francisco Guerrero, si quieres comentar algo, o Ana, no sé quién siga.
Solo agradecerle nuevamente su gran plática al doctor Parsons y su gran disposición para apoyarnos a AMENA este año. Entonces, y le cedo la palabra a Anita.
Muchas gracias, Francisco. Pues igualmente yo de mi parte agradecer al doctor Sergio Fernández por su trabajo como moderador, al doctor Carl Parsons por estar aquí, darnos su tiempo y la excelente información que nos presentó. E igualmente agradecer a la empresa Elanco por darnos el patrocinio para contar con la presencia del doctor Parsons, con la traducción simultánea de este evento. Les dejé por ahí en el chat, thank you, Dr. Parsons. Les dejé por ahí en el chat unos enlaces de interés para nosotros, para todos. El primero es un enlace a contestar una encuesta de este seminario. Les agradecemos que la contesten. Nos ayuda para saber la dirección de nuestros siguientes seminarios. Igualmente dejarles la invitación para el seminario que tendremos la próxima semana. Este es un seminario de la industria. Es presentado por la empresa APC. El tema general es seguridad del plasma atomizado como herramienta en la salud de los cerdos. Vamos a tener las presentaciones del doctor Javier Polo con razones por las que el plasma es seguro. Y del maestro en ciencias Luis Rangel, el plasma puede beneficiar la salud de los cerdos en cualquier etapa de producción. ahí tienen el enlace para que se vayan registrando y los esperamos la siguiente semana, el martes 20 de abril a las 5 de la tarde. Igualmente, invitarlos a nuestro siguiente seminario de nutrición. Este es el lunes 26 de abril, con el tema Importancia del manejo de ensilajes en la dieta del ganado lechero con el doctor Jesús Olmos. Y pedirles que vayan apartando las fechas del martes 4 de mayo y el martes 18 de mayo, donde tendremos más seminarios de la industria. Igual tenemos algunas fechas disponibles, por si es de su interés hacer uno de estos eventos, pues me manden un correo por favor a administracion@amena.mx. Y finalmente dejarles el enlace de nuestro canal de YouTube donde subimos las grabaciones de estos seminarios. Por ahí tuvimos algunos ligeros problemas con los últimos videos, pero ya deben de estar la próxima semana en nuestro canal. Entonces, pues muchas gracias a todos por estar aquí con nosotros, por acompañarnos y pues los esperamos en nuestros siguientes seminarios si son de su interés.